is to talk about wave reflections. One thing I'm going to go to here in a little bit, and it would be really helpful for you to open up this link right here. I'm going to ask that you guys understand 4 different wave reflections, and 2 of them are very similar to each other, so it's really not a ton to remember, but the big ones are the first 2 that we have to understand. Okay, so we have a fixed end reflection and a free end reflection. Then we have to understand less to more dense, and then more to less dense. These diagrams down here at the bottom illustrate less to more dense and more dense to less dense. But we'll come back to those here in a little bit. Okay, so if we click on this link, and we have to scroll down just a little bit, this calls fixed or the fixed end reflections. It'll say reflection from a hard boundary. But really the one thing I want us to understand, and if we think about the standing wave pattern that we saw yesterday, this kind of makes sense. In a fixed end or hard boundary, the displacement remains 0 and the reflected wave changes its polarity or basically just undergoes a 180 phase shift. So notice in this diagram right here, the incident wave's coming in and it has a wave crest. When it reflects off of the fixed end boundary, it ends up being 180 degrees out of phase when it reflects. So if you can imagine what standing waves do, one wave continues to propagate through another, and I'll show you one of these here in a little bit. But the incident wave, the reflected wave flips over, and then it continues to propagate back and forth along the boundary. If we have a free end reflection, so imagine having a rope attached to the wall on the fixed end, and on the free end we've got it on a ring that's able to go up and down on a ring stand. Notice that the reflected wave is perfectly in phase with the incident wave coming in, and when these 2 waves combine at the pivot point, the amplitude ends up being twice as great. So the amplitude ends up here for an instant as the 2 waveforms overlap. So what you get here is a constructive interference, and what you get here on the fixed end reflection, you have an instant where you have destructive interference. Okay, so the last 2 types, and we can kind of scroll down through this. If we're going from a low dense media, so assume that this is like a really thin, light piece of string, and then you got a thicker rope here, and then you got your wall. If we go from a less dense to more dense media, at this point, part of the wave will reflect and part of the wave will continue to propagate, or we can say it transmits through the thicker rope. Notice when less dense to more dense, the wave reflection treats this just like a fixed end reflection so that it flips over 180 degrees, while the transmitted wave is still in phase with the incident wave. So there is no flip for this waveform that continues to propagate. If we're going from a high dense to a less dense media, now this is very similar to a free end reflection. Notice now the reflected wave is still in phase with the incident wave, and the wave that is transmitted is also in phase with it. So no phase change at all on the reflection. Okay, so once again, as we go back through these, the fixed end reflection and the low dense to high dense media are very similar, and the free end reflection is very similar to the high dense to low dense reflection. Okay, so what I want to show is real quick. Oops, I need to restart this thing. Got it going all over the place. Okay, so I'm going to put this link on my website, and I may end up putting it in OneNote after I'm done this. It just depends on how much time I have. Okay, one thing I wanted to kind of walk us through is talking about the individual waveforms and then show you a quick standing wave pattern. This simulation is not perfect to do that, but we can get it for at least 1 cycle so that you can kind of understand what the standing wave meant from yesterday. Okay, so if I send a single wave pulse in, and notice I have a fixed end reflection. Both ends now are fixed, so this waveform is going to make a 180 phase shift on each one of the reflections. Okay, if I get it close and pause it and take it step by step through, notice we have this point right here where we have complete destructive interference just for an instant. This point is when the front half of this triangle wave has already flipped over and the back half is still moving to the right. And when those two halves of the waves overlap, you end up with a destructive interference pattern. As we continue to let it propagate on, then it returns back to its original amplitude and continues to propagate through. So one thing to understand about this, it almost looks like, and it would be real tempting to say that this waveform has no energy. It would have no energy if the waveform just dampened and it came to a stop. But we know it still has energy even though it doesn't have an amplitude here, because once the destructive interference pattern continues to move, then you end up with the original wave crest. Okay? What would happen for energy being lost if I change this dampening, notice the waveform diminishes to 0 over time. Okay? So dampening effects is the only thing that is going to affect the amount of energy in the wave. Okay? So let's go ahead and change this to a loose end or a free end reflection. Now we should be able to see that the reflected wave is in phase and that the amplitude increases and doubles for just an instant as the front half and the back half of the wave are overlapped. Okay? So if I send one wave pulse, it goes back, and then notice it flips over for the free or fixed end. And then it flips back over and so on. And it continues to propagate along the length of the string. It gets a little bit complex, and I know we struggled a little bit yesterday with trying to do some of the combinations of waves. I'm going to go ahead and slow motion this down. Now let's say I had 2 wave pulses. So I add a wave pulse here, wait a half a count, and add another one. Notice when these 2 waves meet right here, you still have your original wave has flipped over. This wave is the incident one. So you have a 180-degree phase shift with these 2 waves. As I step this forward and these 2 waveforms begin to completely overlap, notice that we have complete destructive interference. So both waves were exactly 180 degrees out of phase. Once again, energy is still conserved. There's still energy in that string. It's just not showing up as a waveform. What will happen when I hit play is the waves will continue to propagate outward and reverse on themselves again. And we have another interference pattern as that waveform continues. Okay? This is something you're going to have to practice on so that you guys can end up drawing these when these 2 waveforms are superimposed. Once again, just add point by point when you have to overlap them. Okay? Alright, last thing I'm going to show on this is to change this to oscillation mode. And like I said, this isn't perfect, so I'm going to pause it when it gets to this point. Once these waves begin to propagate in the other direction, notice the green dots now that the 2 waves have passed through. These green dots are stationary, so these are your nodes on your standing wave pattern. The only thing different is this one's just going a lot slower than the one I showed you yesterday, because we really couldn't see the upward and downward oscillations. All you could see is the points where it wasn't moving, and then it looked like a blur as these 2 points were going up and down. Okay? So I'll restart this. Like I said, you get past a couple of waveforms and it starts to get real sloppy. But we can definitely see it. So pay attention to the green dots on this as the waves begin to overlap and reflect. And there's your standing wave pattern that is going to form from that. Okay? Like I said, if we keep going past there, this thing gets to be a jumbled mess a little bit. And that's more of what happens when they start getting out of phase with each other. So it'll come back in phase here in a second, but it's still kind of messy. Okay? So once again, you can see the standing wave pattern reformed right there. Okay, so I am going to go back to OneNote, if I can find this on my screen here. All right, so I talked about the fixed in, free in, less dense to more, and more dense to less. I'm getting tongue tied. You can go ahead and read through this and make sure that you understand it. Okay, so the next thing I want to talk about, and I'm going to, once again, I'll do these practice problems on the board in the next video. Speed of sound and speed of a wave on a string. So what we're going to get into on Friday is talking a little bit more about musical instruments, and we can talk about musical instruments that are either stringed or open tubed instruments. Okay, I got 5% power left here, so I think I can make it. When we are talking about the speed of sound, and we're talking about an open tube or a closed tube musical instrument, we have to base this speed on a couple of different things, because the speed of sound will change depending on what's going on. So the speed of sound simply depends on the density and elasticity of the medium and the temperature of the medium. So first of all, the density and elasticity. Typically, and we won't get into all of the details because there's a lot of stuff to think about here, but all I'm asking you to understand is that sound travels faster through solids than liquids than through gases. So for example, sound travels at about 5,500 meters per second through a chunk of steel. So those waveforms, because it's a more dense media, that energy can propagate a lot faster than it can through air because the molecules are spread so far apart. Okay, which, if you don't believe me, just you can stick your head down on a railroad track and I'll hit it with a sledgehammer and you'll understand real quick how that happens. Okay, same thing happens through water, 1,500 meters per second approximately through water, and then 340 meters per second through air, but this is at just normal room temperature, which is approximately 21.5 or so degrees Celsius. So since we are going to be dealing with musical instruments and closed and open tubes, and most of this stuff is going to be dealt with in the air, unless we want to play underwater, the greater temperatures will result in an overall increased speed of sound, so we need to be able to calculate what this actual speed of sound through air is going to be. Okay, so this is a really easy equation. In air, the speed of sound is 331 meters per second, so at 0 degrees Celsius, the speed of sound is 331. As the temperature increases, the speed of sound will increase by increments of 0.6 meters per second for each temperature change. Okay, where T, once again, this is going to be measured in degrees Celsius, not in degree Fahrenheit. Okay, once again, I'll come back to the sample problem here in a little bit. Okay, when we're talking about stringed instruments, and obviously we can imagine a guitar here, the wave speed is dependent on the tension in the string and a term called linear mass density. And don't make this any harder. And I'm not going to ask you guys to calculate linear mass density or anything. But once again, remember, we are kind of focusing on AP exam stuff here. This term showed up on an AP exam several times. They've given this equation. It's not on the AP equation sheet, so I wanted to make sure that we've at least seen it. Linear mass density is really simple. A really thick, fat string that's heavy, well, it's going to have a pretty high linear density because the mass is going to be pretty big and the length is going to be pretty short. Okay, whereas a little thread is going to have a very small linear mass density. This also, like I said, we can tie this back into the guitar strings. This is another reason why we use smaller strings to play higher note or higher pitch frequencies than the bigger, thicker strings. So when we're talking about speed of sound, the speed of sound is dependent on the temperature of the air and the density of the air. We can factor that in too. When we're talking about speed on a string, it is simply an actual physical intrinsic property of the string itself. So even though the calculation is wavelength times frequency, the speed is going to stay constant as long as I keep a constant tension in the string and I don't change the string. What's going to change it is if I add more tension to it. So on a guitar string, if I wind it tighter, I'm probably not going to overstretch the string to change the linear density too much, but adding tension to it is going to increase the speed, and once it increases the speed, then the wavelength and the frequency will change as well. Okay? One thing is kind of hard to understand, and I will keep this simple. The demonstration I did yesterday, I used that flexible string that was on the wave generator. Most of these that we're going to be thinking about, just imagine having an actual physical string that does